This lecture is an introduction to sequences and series. A sequence is sort of a list of numbers. The first one would be a sub 1, then a sub 2 is the next, a sub 3, and so on. Whereas a series is when you add all these together. So a sub 1 plus a sub 2 plus a sub 3, and so on. So the sequence is the list of numbers. The series is when you sum up those numbers, those terms. And one way to think of a sequence is as a discrete function. So here would be sort of a graph of the first four terms of a sequence. So a sub 1 is equal to 5, a sub 2 is 9, a sub 3 is 13, a sub 4 is 17, and here we have our n, which is our term number, and here we have a sub n, which is the value of the term, and I just plot them. So as you can see, it's just a discrete function, and where the domain of the function is the natural numbers. You can start at 1 and go up from there. You never have fractional term numbers or anything like that. Okay, writing terms of a sequence. To evaluate the terms of a sequence, you just plug numbers in, starting with 1. And so if a sub n is 3n minus 2, plug in 1 for the first term, you get 1. Plug in 2, you get 4, and so on. Here we have 3 plus negative 1 to the n. So we plug in 1 for the first term, 3 minus 1 is 2, 1 for the second term, 3 plus 1 is 4, and so on. So not too much to write in the terms of a sequence. Again, if you want to write the terms of a sequence, you plug in the term number that you want. So plugging in 1, 2, 3, 4, 5. What's a little bit more challenging than finding the terms, writing the terms of a sequence from the formula for the nth term is to do the opposite. That is, find the nth term of a sequence given the terms in a sequence. And so this is a pattern recognition idea. We're going up by 2 every time. So it's sort of you can think of it as linear with the slope of 2, so that's why we can come up with the 2n. And the reason we put the minus 1 in is because if you just made it 2n, then your first term would be 2, and your second term would be 4. But we want, say, 1 and 3, so we've got to subtract 1. Over here, 2, 5, 10, 7, that's 1 more than the squares of numbers, 1, 4, 9, 16, so n squared plus 1. So sometimes it can be a challenge to find that pattern. It just takes some experience. But there's a few tricks to look for. Fibonacci sequence is another way to get a sequence. It's a recursive sequence, so each term is based on previous ones. In this case, each term for the Fibonacci sequence is the sum of the previous 2. So you start with 1s, and then to get the next term, you sum the previous 2. So 1 plus 1 is 2, 1 plus 2 is 3, 2 and 3 is 5, and so on. Factorial notation is important in sequences and series because it's a very compact way of writing some important mathematics. So in this case, n factorial is n times n minus 1, n minus 2, all the way down to 1. 0 factorial is defined as 1. Later in advanced single variable calculus, you can talk about half factorials, fractional factorials. You can see why 0 factorial is 1. It's complicated stuff that you'll get to later. But this is generally how you express factorials, how you evaluate them. If you want to write the terms of a sequence involving factorials, it's no different than anything you've done before. This time we're beginning with n equals 0 as opposed to n equals 1. So you plug in 0, 2 to the 0 over 0 factorial, 2 to the 0 is 1, 0 factorial is 1. Plug in 1, plug in 2, and so on, just evaluate them. Simplifying factorial expressions. Because 8 factorial is 8 all the way down to 1, 6 factorial is 6 all the way down to 1, you can cancel everything out. So when you cancel out the 6 factorial with the 8 factorial, you're left with 7 times 8, and then 7 times 8 over 2 factorial is 7 times 8 over 2, which is just 28. So that's the idea behind all three of these, is canceling off all the lower ones that go down to 1. So n factorial over n minus 1 factorial, you have to realize that n factorial is n times n minus 1 and all the way down. And so you get rid of the n minus 1 factorial top and bottom, you're just left with n. Okay, summation notation or sigma notation, capital sigma for sum. This is important. This is now getting into series instead of just sequences. So now we're adding the terms. We're not just listing them. So here's our lower limit, and here's our upper limit for our summation, and I is our index. So if we want to evaluate this, 3i is our general term, and we plug in 1 through 5. So we plug in 1, 3 times 1, plug in 2, 3 times 2, then 3, 4, and 5, so 1 up through 5 by 1s, and you add all those up. For this one here, you're going to go from 3 to 6, so you plug in 3 into the formula, plug in 4, plug in 5, plug in 6, so lower limit to upper limit, evaluate it, add it all up, and finally this one down here, 0 up to 8, you plug in for factorials, and it's true that as you go towards infinity, this is actually equal to e, which is another formula you'll be able to prove in advanced single variable calculus. Here are some properties of summations. If you have a constant, it's just the constant times the how far the index is going. This is saying that basically you can take a scalar multiple and put it in front. A summation of a sum is the sum of the summation, so you can split it up, and same with differences. And so this leads to the idea of a series, where you're adding up all the terms. A finite series is one that has a finite number of terms, and it's a partial sum, so you're only taking a certain number of terms, whereas an infinite series, your upper limit is infinity, so you have an infinite number of terms, and this is no longer a partial sum, it's an entire sum. It's not a finite series, it's an infinite series. So finding the sum of a series, we want to find the third partial sum and the overall sum. Well, a couple different ways to do this. To find the third partial sum, we just want to go from 1 to 3, so we evaluate it for 1, 2, and 3, and we add all those up. When you do it infinite series, you can see that the pattern is becoming 0.333, which is equal to a third. Later on, we'll get to the concept of a geometric series, and you'll be able to see why this is also equal to 1/3. While we're talking about sigma notation, let me show you this idea too. This is changing your index value. Sometimes it's useful to change the index value. Here we're going from 0 to 5 of 2i minus 1. We can change our index value from 0 to 5 to 2 to 7. So we add 2 here and here, and we subtract 2 for I, and then we simplify this, and we get 2 to 7 of 2i minus 5. So these are equivalent expressions. Okay, and then you can apply these sorts of things when you have, say, this is a population model, when you've got a population modeled according to this general term, and you want to find out what the population would be. You're just evaluating that sequence. Okay, some practice problems. All right, evaluating terms for this sequence. So you plug in 1, -2 to the first is -2, to the second, -2 squared is 4, and so on. So this is called an alternating sequence because the terms change sign every time. All right, this one we're trying to take these terms of a sequence and get the general term. So this is a pattern recognition, and the way to do it is to split it up. We notice 3 things. It alternates, plus, minus, plus, minus. There's a numerator part and a denominator part, so you should treat it all separately. So the alternating part is always going to be -1 to either the nth or the n plus first or n minus first. N plus first, n minus first are the same though. And we want to start positive, so the idea is we're going to start with n is equal to 1. So if we're going to start with n equals 1, then we've got to do -1 to the second or -1 to the 0 to make sure we start positive. So that takes care of the alternating. The numerator is doubling every time, so that's 2 to a power, and we're going to do 2 to the n minus 1 because if we just did 2 to the n, we would have started with 2. We want to start with 1. And the denominator is multiplied by 3 every time, but we start with 3 to the first power, so that'll just be 3 to the n. And now we stick the whole thing together. So we've got our alternating, we've got our numerator, we've got our denominator, and this is sufficient. You could leave it like this, however, to make it look a little prettier. You can combine some things. These are the same exponents. You can put them together. And now we can maybe get the same exponent there by rewriting 3 to the n as 3 times 3 to the n minus 1. I'll take the 3 out as a 1/3, and then I can put all that together. But these are all equivalent to each other. Okay, simplifying factorials. N plus 2 factorial is n plus 2 times n plus 1 times n minus 1, all the way down to 1. N factorial is n minus 1, all the way down to 1. And so clearly we have a lot canceling out here. All of this cancels all of this, and you're just left with those two guys, which you can either leave or multiply out. Now we want to evaluate this sum, so we're going to go from 0 to 5. First I brought the 3 out. You don't have to do that, but I think it makes it a little simpler. So you bring the 3 out in front, and then you're evaluating for 0 through 5. So 0 squared, plus 1 squared, plus 2 squared, plus 3 squared, 4 squared, and 5 squared. Add them all up. 3 times 55 is 165. And now this is again a pattern recognition. So we've got no alternating. We've got a numerator and a denominator. We want to put it in summation notation. That's the idea here, summation notation. So the reason I went from 1 to 10 is because I see that I have 1 here and 10 here, and it's going 1, 2, 3, so it's going by ones. So I thought that would be convenient to go 1 to 10. Not necessary, but convenient. And then now the numerator is always 1. The denominator is just whatever your index is. So that'll just be n, but then this other piece of the denominator is always 2 more. So n and n plus 2. So this then is your summation, which represents this sum. So it's a pattern recognition, not for sequences, but for series, to get this general term and then also get your index values.